at the use of PCA beyond Gaussian data, right? We were looking at mixtures of Gaussians, and we also looked at hidden Markov models. And I said broadly the idea from spectral methods is how spectral decompositions can help us get dimensionality reduction, can help us achieve better separation between signal and noise, or better efficiency in terms of samples required to learn, right? So these are all benefits we can obtain from spectral methods. So I think when I said spectral methods, it broadly means different kinds of spectral decomposition, right? So eigen decomposition, singular value decomposition. So depending on the scenario, the actual computation, and which matrix on which this is computed may change slightly. But broadly, that's the idea of spectral methods, in particular spectral methods based on matrix factorization. Okay, so when we said Gaussian mixtures, right, like in short, GMM stands for Gaussian mixture models, the main idea was spectral methods can help us achieve dimensionality reduction if the components lie in some lower dimensional space, right, compared to the ambient dimension. So the component means lie in low dimensional space, or they have a smaller number of components compared to the size of data, right? So if there are k mixtures in d dimensions, we said when k is far less than d, this is high dimensional data, right, but living in some latent lower dimension. So in that case, if you do spectral decomposition, in particular if you do PCA, you can reduce the dimension of the data and project it onto the subspace of the means. Right? So after that, you can do spectral clustering and any other method to further try to separate the components. So this is known as spectral clustering. There's a lot of literature in this topic on how to both analyze this and also, of course, use this in practice, right? So you start PCA, then you do clustering in the lower dimensional space. And we saw justification for this from looking at the moments, right? So when we wrote down the covariance matrix of data, we saw how projecting it onto a lower dimensions means we can get access to the subspace of the means, and hence by doing clustering in this subspace, you can get better separation, right, in terms of because those correspond to the subspace of the means. You know, the other dimensions do not matter when you try to separate the components. Because in this assumption we had, they were all spherical Gaussians, right? So the variance is only hurting you when you try to separate the components. Okay, so PCA helps you reduce the variance. Does that make sense? Any questions here? So in this case, we saw PCA can get us to the subspace of the means, but not actually give us the means, right? So we discussed a simple fact: if you have access to the product of a matrix and its transpose, that doesn't mean you know the actual matrix, right? Because you can always have a rotation matrix in between, and hence what you get is only the subspace of A and not A itself, right? So you have this ambiguity, and you cannot resolve unless you have more information. So if all I have is this product, I cannot tell what A is. And essentially when you're doing PCA, right, you have that ambiguity. So you have to get some other kind of information to further resolve that. And in spectral clustering, the way to resolve it was try to do either k-means or EM, right, which essentially means you're trying to make a judgment of which component each sample belongs to, and you go back and forth. But to do that, you have to have enough separation. If everything is very high variance and all the components are mixed up, you will make errors, very large errors in terms of trying to determine which component the samples belong to. And hence, in that case, EM will not converge, right? We won't get to the true underlying solution of Gaussian mixture model, and hence there's no guarantee it'll work. And so that was the downside of using just the matrix factorization method. And today what we'll do is take that further and ask, can we do something more? Right, so is there a way to recover the component means even when there is no separation? I have a very large variance, but I have samples from this distribution, right, from this mixture of Gaussians. Can I recover the model parameters? So we'll address that today using tensor methods. Okay, so that's the plan. Any questions so far? So what I'll do is I'll have a recap of Gaussian mixture model and jump to tensors. I think in the last class I had like just a tiny part of hidden Markov model that wasn't covered. I'll get back to that later, but it's also, we can also see in that example how tensors can help us recover the model parameters and not just an observable representation, right, like the one I discussed in the previous class. So keep that aside, we'll come back to hidden Markov model, but let's first focus on Gaussian mixtures. Okay, so how did we represent these Gaussian mixtures in the previous classes? We had both the selection variable as well as, right, we wanted to incorporate the variance of the Gaussian, which we assumed to be simple spherical, model. So to do that, we had this, right, a linear representation. So we had the assumption that the noise was spherical Gaussian. And for simplicity, we assumed it just had the same variance for all the components, right? So we can relax all these assumptions, but we'll limit to this for the ease of discussion. And the primary aspect that I kept emphasizing a lot on was to represent discrete random variables as vectors. Right, so you can think of them as taking standard basis vectors as their values, right? So the sample space for the selection variable is all the standard basis vectors. Right, so when I have a discrete or categorical random variable, I can assign any k categories. But in this case, I make this particular choice of them being standard basis. And we've seen that this is convenient, right? Because I can now write down the distribution of this variable h in terms of the expectations. So all probabilities turn into expectations when I do this representation, right? Because expectation of h, right, let's say it's this vector w, which means the ith entry is the probability of selecting the ith component, right? So the information is easily encoded in this vector representation. Okay? Right, and we also had other notations, the sample mean, the mean of the population mean of the mixture of Gaussian, we can write it as expectation of, right, A times H, which is nothing but it's the weighted combination of the mean of the components. So this matrix A was collecting the component means, right? So we had this as the combination of the. And I think I made a comment in the previous classes as well. We'll try to avoid summation as much as possible and write it as products, right? Matrix products or matrix vector products. So that will make it convenient as we manipulate more complicated quantities. So this was the first moment, right? First order moment. And then we did the second order moment. We wrote down the covariance matrix, but we can also just write down the correlation matrix, right? So I can look at both. So when I look at correlation matrix, what do I get? Can someone tell me the answer? Right, I mean, I can just expand this and look at all the terms, right? So what is the first term equal to? The product of this with itself. What does it reduce to? Right, so I can write it as, I can take the expectation inside, I can write this, right? What is this equal to? What are the values H takes? Can someone tell me the answer? One expectation of, so what is H, what are the values, what are the different values H takes? It's here, right? So it'll be some basis vector transpose, right? With what probability will it take the value equal to this ith basis vector? I just have it here, right? Wi, right? That's the probability. Then I'm summing it up. Okay, I mean, for a lot of you, it's very unusual to think of discrete random variables through this vector notation. That's why I'm going through this multiple times. Okay, it may seem unusual. Excuse me. Right? So that's why I write it down. When you write down what is HH transpose, right, it can only take on these standard basis vectors. So I can expand it this way. So as I said, we don't want to write in terms of summation. What is the overall simplification of this?
Diagonal of W.
Right, so because these are just, right, having only the non-zero entries are along the diagonal, right? So because each one is just rank 1, right, and equal to one of the diagonals. So we'll have this notation right? Any questions here? It's okay if this is confusing because it usually is, so that's why I'm going slow here. But if you don't ask me, I have no idea whether you got it or not. Is it clear? Is it clear to you? Right? Because you don't want to think of them, right, as just scalar random variables. You want to think of them in terms of these vectors. Right? That's the difference. Okay, because we are so used to thinking of discrete random variables taking some discrete values, right, or categorical taking some categories. But instead we'll rewrite them as taking on standard basis vectors. Okay, it becomes convenient to manipulate. I mean, in the end you get the same answer no matter what. Right? This just makes it convenient as we go to especially higher order moments, right? That's the reason we use this. And the other thing I like about this notation is, in this kind of representation, I don't have to worry about whether it's discrete or continuous. I can just keep taking expectations, right? Because otherwise, when you're doing all discrete random variables, you're looking at probabilities. When you're looking at continuous, you want to look at PDF and then all the moments, right? So we just want one representation of moments for both, and this makes it convenient to evaluate moments directly. Okay, and if you recall in the previous class, even for hidden Markov models, that's why we use this representation, and we also looked at these joint probability matrices, right? So you can also think of using the representations there. Okay, so if I have this, what is, I can now replace that here. Right, and then I have the noise term, of course. Right? I mean, here again you can interpret this, right, as with probability Wi, you select ith component. In that case, this correlation is expressed as just the mean vector and its transpose. Right, so simply that's very intuitive, right, because the correlation, right, the mean contribution will be that vector, right, and its transpose, but with probability Wi. Okay? Any questions here? We're going slow here because the very next thing we'll ask is, what if I now look at third order moment? Can we write this down? So if you're not clear here, we can't proceed. Right? I'm sure you've thought about, right, moments of a distribution and thought about correlations, but you probably, do not work with vectors and matrices, right, and moments for that. So that's why it's a bit more involved. Okay, but hopefully this makes sense. So everyone's on board here? Good. Okay, so now what about the third order moment? How should I proceed? What do you think?
So instead of using x transpose x, you can have x output x output x.
Right, so we need the notion of order product, right? So, but first of all, intuitively, why should I look at third order moments? Why not stop at the first two moments?
Does he model everything as a Gaussian that way?
Exactly, right? So if you only limit to first two moments, it's either Gaussian or if it's, or it's a categorical variable, right? In which case it's just the first moment. Those are the only distributions that can be modeled just with that information, right? This is not sufficient, right, for if you want to model more complex distributions. And so the natural thing is to, go to higher order moments, and for an arbitrary distribution, it could be, right, you could just keep going to higher order moments and you have more information, right? But the hope is, again, for nice parametric families, maybe just low order moments will suffice, and, you find a way to extend these notions of PCA to somewhat more complicated class, but still classes you can reason about. Right, so that's the idea of thinking of going beyond just the first two moments. Okay, so if you recall, we have the moment generating function, right? So, and if you recall the theorem from basic probability, it says that the moments are equivalent. If you take all the moments, right? Rather, you take the moment generating function that completely characterizes the distribution. So if you told me everything about the moments, that uniquely pins down a distribution. But of course, in practice, we won't have these exact distribution or exact moments, right? These are called population moments, because if I had the entire infinite set of samples, I can exactly compute this. But then when I have finite set of samples, I will have deviations, right? From this value, it won't be exactly this. But that's where there are concentration bounds, and in the first class we briefly mentioned that. And that can also help you tell that you don't have a lot of perturbation and still you can deal with finite sample issues as well. Right? That's another issue. Okay, so we'll now go to third order moment. So in order to think about the third order moment, right, we want to first kind of go into asking what is the second order moment telling us, right? So since X is a vector, right, this XX transpose, this is a matrix, right? So what do different entries of this matrix tell me? If I look at ijth entry of this correlation matrix, what does it tell me? For any random vector, right? So if I have any random vector x and I look at the correlation matrix, right, the pairwise correlation matrix, this is nothing but it's looking at the correlation of the ith and jth entry of that random vector. Right? So, this is a simple fact, I'm just writing it out. Right? So, this is the interpretation, right? When you write down your pairwise correlation matrix, what you're doing is each entry is telling you what is the value of correlation of ijth entry. Right? You're just collecting all those correlations together. So if I think of this interpretation, how can I write down the correlation of, right, three entries together? That would be the third order moment, right? So I can make the natural extension here to say, now I'm going to write, this is the outer product notation, right? And that we can use it to extend what we had before. So instead of just two entries, we'll look at correlation of triplets of entries. Okay? So now instead of this, I'm going to extend to one more dimension. So it's a cube, right? So I'll have all these entries across every dimension. And so I'll now look at, right, index over all the 3 entries, all the 3 what we'll call modes. Sorry, this notation here. So, right? And we'll record them in a tensor. Okay, so hopefully this is a right definition you can follow immediately. Okay, so this is the interpretation of the outer product, right? So for the definition, right, I can look at outer product of, let's say, if there's any 2 of them, right, that means it's just that the ijth entry is equal to the product of ith entry of the first vector and the jth entry of the second vector. If there are 3 of them, similarly, I have that extension. Right, I can extend it for any number of modes, right? So the modes are the different dimensions here. So the different indices we have, each one will call it a mode. So usually this is mode 1, mode 2, mode 3, and so on. Okay, so for matrix it was rows and columns, right? Now we have more dimensions. Okay, so this is the definition of an outer product, right? And this we'll also call it as a rank 1 tensor. Because you can see in the case of the matrix, which is a special case, right? So matrix is now a second order tensor, right? So matrix is a special case, tensor is any order. Okay, so in the case of the matrix, this outer product is nothing but, right, the rank 1 matrix. Right, so this you're aware of. So usually when I've written ABC here, these are all vectors. Okay? So I can extend the notion of rank 1 to tensors as well. Okay, and the interpretation through correlations, I think, makes it convenient to also introduce the definitions. That's why I first talked about collecting all the correlations, right, in this now third order tensor. And with that, I can also, introduce this notion of outer product. Any questions here? Right? This is a natural now extension to higher order, and now I can, if this is my definition of the third order moment, I can now try to write down what is the third order moment for my mixture of Gaussians. Right? So for the entire vector, it can be complicated. So first I'll just write down what is the third order moment of this selection variable h. So we wrote down what it was for the second order, right? In fact, it was just this diagonal matrix. What do you think will be for the tensor?
The contraction on h, all the h's.
So I haven't introduced contraction, so that means I probably would not require a contraction.
Oh.
I'll come to it later, but just from the guess. Like, what was the special property of this h? It's not some arbitrary random vector, right? It's special. Why is it special? Takes on only the standard basis vectors, right? So that means there are lots of zeros, right? Meaning, in other words, there's lots of entries that are uncorrelated, right? Here, if I wrote down ijth entry, if I is not equal to j, this is just 0. So what do you think will happen in the third order moment? If I have, let's say, ij kth entry, and if I is not equal to j, not equal to k, what is it? 0, right? Okay, so what if I equals j but not equal to k? Still 0, right? So you don't need, so the only thing that will be non-zero is when they're all equal to each other. So what would it be in that case? One of the w's, right? So whatever, let's say this is all the same, that's wi in that case, right? Right, so yes, it's a big tensor, right, because I'm running through all the indices, but they're all 0 except when it's equal. So what do we call this tensor? It's again a diagonal tensor, right, like a diagonal matrix. So if you picture it here, right, the diagonal you see with the cube, the diagonal that runs inside the cube, it's only non-zero along that. Okay, so for this case, we could write this down pretty easily. So I'll rewrite this as, diag with the definition that this is now a diagonal tensor. Okay, so I think it's non-zero only along the diagonal. So now the next thing, right, so, but what I want is not just h, right, for this term I want a times h, right, so meaning the selection variable is picking up a particular mean component with that probability, right, so with probability wi it's picking up ai, right, so that's what we want to have that process. So I'm just going to look at the correlation of now a times h. So what do you think that'll be? So again, let's come back to the matrix, right? So what did we have here? We have it here, right? So for the matrix case, right, we wrote in terms of the matrix product. We also wrote in terms of the summation.
I guess in the summation form,
Yeah.
like the sum of wi and then ai, like product. AI.
Exactly, right? So that's good. So that means my explanation's working. So with probability wi, right, takes the value ai and right, and that's rank 1, right? So, and then you're summing over all the possibilities, that's why the summation. Okay? I mean, you can't really write it in this matrix product form, right? Because we don't kind of, that's where we'll have contraction and other notations for general cases. But this is, I think, a more convenient notation for writing out this expression. So it makes a lot of sense in terms of interpretation, right? In each sample, right, the only possibility is one of the k components, right? They can't occur together. It can be only one of them, right? So once I make the selection its ith component, right, you only get ai for all the 3 modes. And then you have the expectation that you sum over all the possibilities of h, right? That's how you get this. Okay, so if there are k components, we have now k such rank 1 elements, right? So it's summation of k rank 1 tensors, right? Each one is rank 1, we're summing over k of them. So this is called like rank k tensor, and in particular this form of rank is called CP rank. So it stands for Kandikaup, canonical decomposition, parallel factorization. It's a long form of that. So I wrote down CP rank because there isn't one notion of rank in tensors as in matrices. Right, so if you recall your matrix rank definition, I can write down, right, so let's say I have a matrix M, I can write down in terms of singular decomposition, right? So this is nothing but looking at sum of rank 1 components, right? This is the analogy. I mean, here it's symmetric, but again, you can also extend this to asymmetric, right? So this was the notion of rank in matrix, but I can also just factorize it into 2 other matrices, right? And as long as this one, it's rank k, if let's say this, I have like tall and thin, right? So if I can factorize it in terms of lower rank matrices, right? That's the smallest of that is also the rank of the product. So in the matrix case, these 2 are equivalent, right? I can write in terms of sum of rank 1 components. I can factorize them into smaller matrices. The 2 are equivalent, but that's not the case with higher order tensors. They give rise to different notions of rank.
Is there a generalization of the rank nullity theorem in CP rank?
The rank?
Nullity theorem?
So in terms of, you mean there is a null space?
Yeah.
Anything, you mean there is...
Is there like some kind of intuition of CP rank in that kind of regard?
So it's no longer linear,
yeah.
Right? So that's the first thing that goes out of the window. And in a minute, I'll talk about that. So I will talk about, like matrix algebra relies a lot on linearity. So a lot of that will not be true with tensors. Okay? Yeah.
Is that still more linear?
Right. So, the notion of multilinearity comes because I can have linearity in each of the modes, right? In this case, it's symmetric. You don't have that. If you just had asymmetric ones, right, if you contract with different components, then you have multilinearity, right? So it depends on the optimization problem. We haven't come to that yet. So I haven't defined it yet. Give me a minute. I'll do that. Okay? But any questions here, right? So I've defined the rank in terms of sum of rank k components. Sorry, each rank 1 together, it's rank k. Okay, so the question remains, can I find each of the components? Right, so in case of matrices, we do eigen decomposition, when this was symmetric. When this was asymmetric, we'd do this SVD, we'd get the components. And, of course, there are underlying algorithms for that, right? We didn't kind of go into details of why they work, but now we'll have to peer into them, right? So what made matrix decomposition work? And can we hope to take it to tensors? Right. So we'll focus on trying to find this decomposition. By the way, I ignored the noise component because if you knew the noise and its identity, you can cancel it out, right? So that's not as crucial here. The main question is, can you recover the individual A from these from this decomposition, right? And we said in the case of matrix, you only get the subspace, you don't get the actual entries. Because these A are not orthogonal in general, right? They are just any general vectors. These are just means of components, so there's no reason for them to be orthogonal. Okay, if you just did matrix decomposition on this, right? You would get the subspace of A, but you don't know what the actual A vectors are. So the question is this giving us more information, right, this third order moment, and can I recover the A's from this? So what's your intuition? Is there more information here? If so, why? If not, why not? Right, because earlier I had sum of Wi, right, AI, right? I took the outer product twice, now I'm taking outer product thrice. So would it have more information? If so, why? Just intuition. What's changing from here to here? What's the size of this? Let's say this was D by D, right? So this is now D by D matrix. What's the size of this? It's D cubed, right? So D by D by D. So there are more entries here for sure, right, compared to here. Order D more entries, right? So it's order D times more entries. So at least the hope is there's more information. You know, I have now a bigger object compared to this. The question is there more information in there? And potentially there is, right? Because we are not just looking at from this outer product we get like product of entries of 2 of them, but now we are also getting entries of 3 of them together, right? So there is now this higher order correlation information available. Okay, so potentially more information and also more constraints, because if I want this to be a rank K tensor, right, I'm putting constraints on it. This is not just an arbitrary tensor. Okay, so that's the hope. I'm getting more information now. I'm adding these constraints of this being low rank. Can I recover the components? Okay, and so to now ask, why is it possible to recover and what are the algorithms? We'll go back to looking at the optimization landscape for matrix eigendecomposition. And then we'll come back to tensors. We have to keep going back and forth, because unless we understand the matrix world completely, we cannot hope to extend it to tensors. Any questions so far? Yeah, all good? So we're now going back to matrices. We had this matrix, right? Let's say symmetric matrix. And if you recall, we had the optimization interpretation of the top eigenvector. So what did we say the other day was the optimization formulation to find the top eigenvector? We talked about it extensively, right? What was the formulation for finding the top eigenvector? Rayleigh quotient, right? And the Rayleigh quotient was written as optimizing this quadratic form on the sphere, right? Okay, so now if I have a constraint, what should I do? Should look at the Lagrangian, right? So I should introduce it as a penalty, which is what we'll do now. So I can write this as lambda times . So I'll just add by 2 here, just you'll see in a minute because of the interpretation. Okay, and I'll also make this minus because it doesn't matter, right? I can write it either way. Okay, so this is the Lagrangian. So let me call this Lagrangian on both x and lambda. So, now what I want to do is look at the fixed points of this optimization problem. Right, so if you recall, right, I can ask what are the stationary point where the gradient vanishes. Right, so I can keep looking at critical points at different order, right? This is what I can do with an optimization problem. The intuition is, I can just plot this in one dimension, right? So whenever, it's stationary point, the gradient should vanish, right? So let's look at where the gradient vanishes here. So actually I don't need this half, because here there is 2 as well. So what is the derivative of this with respect to x? Again, it requires, because this is differentiating with respect to a vector, right, it may require you to kind of think a bit more, and also because it's symmetric, right, this will be, there's x transpose m and m times x is the same, so it'll be 2 times that. So, and then there's also 2 here, so they'll go away. So I get this. So what are these points? They are eigenvectors, right? And lambda is in fact the eigenvalue of it. So all the eigenvectors are stationary points of this optimization problem. So recall I set out to only find the top eigenvector, right? But then the gradient vanishes even at all the eigenvectors. So meaning the eigenvectors are stationary points. So that's why if I did this power method, so if you recall the power method, can someone tell me what's the power method for computing the eigenvector, the top eigenvector? What do we do there?
To keep product n to this thing to piece power, so it's like iterative.
Right, so in each iteration, what does it end up? What's the simple computation I do in each iteration?
So I do QR and then Q.
Right, so I guess that's kind of going into the details of, right, maintaining this orthogonal subspace. But if it's just the top one, it's even simpler. I'm not asking for the full eigen decomposition, just the top one. I can just multiply this matrix with some random vector, right, to begin with. I can normalize, and then I can repeat, right? I can also extend this to computing all the eigenvectors, but I want to keep it simple, right? So I'll kind of keep repeating this. Right, so I'm just like, I can start at a random point, I keep multiplying this with the matrix. So if I initialize with an eigenvector, what happens? Just have the answer there.
It'll be stationary.
It'll be stationary, right? So all these are stationary points for this power method, right? So all the eigenvectors here are stationary points, right? So what this is trying to do is essentially a form of gradient ascent, right? So because this is the gradient, right? And then there's normalization because you want it to be on the sphere, right? So what you're seeing is a form of gradient ascent here. It's just that this is infinite step size, right? Because you're completely replacing your previous answer with the next answer. Okay? So so there's that connection, right? So, but from the optimization viewpoint, what we saw was this is the first order condition. And so let's do the same with tensors. So before I go to second order and before I complete that, now what is the analogy of extending this to tensors? Right, because when we wanted to get all the way to computing this kind of decomposition, we want to first start with thinking of the top eigenvector, right? So if I can get that top component, hopefully I can do it one by one and recover the others. So at least I can start with the same intuition here from the matrices. So what should be the analogy for computing the top eigenvector of a tensor? We were maximizing the quadratic form, right? So what should I be maximizing? What was this quadratic form intuitively doing? Someone mentioned a term earlier.
Tensor contraction.
Right? So, so what is this quadratic form intuitively doing, right? It's multiplying with the same vector along both the directions. And it's a symmetric matrix, so the hope is, right, this kind of gives you a measure of energy, right? So, I mean, the idea is now, instead of standard basis, you want to find the right basis to represent the matrix. And the top one has the most energy, right? So this quadratic form was a way to measure energy of the matrix. So in the the most energetic direction. So how can I now go to tensors? So tensor will have now 3 directions. So intuitively what I should do is multiply now all the 3 directions with the same vector, right? So I need the notation, so I'll write it here. So we'll need to extend that notation. So when we wrote x transpose mx, right, so what that's doing is it's looking at, so if I just expand this, right, so it's xi mij xj, right, over ij. So roughly what this is doing is, have this matrix. Now I want to multiply this with these vector, the same vector, right? So I'm just drawing it for you to visualize. So now if I have a tensor, okay, this is my badly distorted cube as the tensor. So intuitively we should do the same, right? We should multiply the tensor along all the 3 directions. So this is my, so that would be the contraction, right? So I'm finally contracting it to a scalar value by multiplying along all the 3 directions. So I'll use this notation for contraction, right? So this is like multiplying along the first mode, second mode, right? Here there were only 2, but here there are 3. So we can write this as, I look at the ijkth entry of my tensor and then multiply it with xi, xj, and xk. Right? So if I want the general notation, let me use different entries here so that you have the definition. Okay, and because we're looking at symmetric tensors here, we'll just use the same vector for all the 3. Okay, so this is the notion of contraction. So we're extending matrix product to more dimensions. So I can also contract tensor with matrices. I can put matrices in here. I could also put other tensors. That's an extension I won't deal with, but the tensor contraction is the most general form, right? So all the matrix products, everything I can write in terms of tensor contraction. And I can have a rich representation of all these computations. So the multilinearity comes from this, right, what Zongi was earlier mentioning. Because now you can see if you contract with these different vectors here, the resulting is one is multilinear with respect to those vectors. Okay, so we also have that interpretation. So if I have this notation, now I have the way to measure the energy of my tensor. I can use that to write out this contraction. And similarly, I can still maximize it on the sphere. Any questions here? Right, so the intuition is, everything from the matrices so far holds also to tensors, right? We saw in both these cases, we want to find a good basis to represent either the matrix or the tensor, right? And the standard basis may not be good, right? Because it doesn't capture which directions have higher energy compared to others. And to do that, in the case of matrix, we contracted the matrix along each of the direction. And because it's symmetric, we use the same vector in each of the direction. And similarly, for a symmetric tensor, I can contract it, and I want the largest value, right? So that would be the most energetic direction. So what would the answer be for this diagonal tensor? If I want to compute the most energetic direction of a diagonal matrix or a diagonal tensor.
The basis vector with the largest.
Exactly, right? So just, many of the intuitions from matrices carry over, right, so far. So you can think of all those cases like that where, if you have, not just diagonal in general, any combination of orthogonal, right, combinations, the top one will be the one directly. You don't have to do any more computation. You can just look up. Okay, so we have this notion. So again, I can write down the Lagrangian as before, right? So I can take the penalty term and incorporate it. So I will So this part remains the same, right, because it's the same constraint as before of being on the sphere. I can always, rescale my Lagrangian, the dual variable. So let me just write it this way so that it's convenient. So I can take now the derivative, right? So I can look at the derivative of my Lagrangian with respect to x. So what would this be equal to? What's the derivative of this first term with respect to x? We can look at this definition, right? So, okay, let me just do this here. So now I want to take the derivative of this with respect to some x. Let me use, I know XL, let me say, Lth component. I can do entry by entry like this, right? I mean, then it should be one of these entries, right? Otherwise, you don't have the derivative. So you can do the math that way, right? So it ends up being, so essentially, right, so in the case of matrix, when you had X transpose MX, right, one of them went away, right? It's symmetric, I can kind of just, the other part is the same, so I just accumulate that. So similarly here, I can kind of take, you know, they're all equivalent, so I'll just write one of them. And here it's identity, so essentially I'm not contracting this mode. And the other part, right, this 2 and 2 cancel, so it's minus 3 lambda. Okay, so when I write down this notation, right, meaning the third dimension or the third mode, I'm not contracting, right? So here in this example, I was contracting with a vector along each of the dimension. In one of them, I don't have that vector, right? I'm not contracting. So the result is a vector. Okay, so if I expand that, I can write this down as, right, I have the indices for 3 of the modes, but I'll only contract 2 of the modes. Okay, so the third one is free, right? So that's why it's a vector. Okay, that's what the expansion looks like.
Should there be an X beside that?
Oh yeah, yeah. Okay, so I want to set this equal to 0, right? So if I set this equal to 0, I can take this 3 out. So what do we have here? If we compare the analogy to the matrix case, what do you see? What do you notice? What's similar? If you compare the two equations, what's similar? Nothing similar? Anyone? What's similar? Does the equation make sense, first of all? Right, I wrote down the expression. Yeah.
I mean, what's similar is like, you still have like a similar form. I guess the only difference is that now you have like D equations where you have this like Dij k thing, and those all have a summation that equals to lambda x.
Mm-hmm. Right, so I guess what's similar is, first of all, you have this kind of equality, right? Like a set of equations to begin with. Okay, that's one simple one. And what's similar is also, of course, the right-hand side, right? So some way what I'm saying is, you know, if I start with a vector x and I do operation on the matrix, right, it stayed stationary, right? I could do this power method, it was the stationary. Similarly, I start with some vector x, and if I operate on the tensor according to this equation, right, so I contract along 2 of the directions of the symmetric tensor, I do not move, right, so I'm stationary. So I have the same interpretation as the matrix power method, right? I can have a tensor power method. So what I do is I take my symmetric tensor. Because it's symmetric, I can pick any two of the directions, right? They're all equivalent. I normalize it, right? Because I want my eigenvector to be normalized. And then I keep repeating this.
Sorry, what is the I here?
I is identity, sorry.
Matrix?
Yeah, it's a matrix. It's identity matrix. So, I mean, I use this notation to say I'm not doing anything here. So in my notation, I could multiply each of the directions or each of the modes using a vector or a matrix, right? More generally, it's a matrix, right? So if I say identity, I'm not doing anything. I mean, some papers also have the notation of just dot here. So when you say dot, that means I'm not touching that mode, right? I'm not operating on that mode. I'm not contracting that mode. So these are equivalent notations. Right, so I can think of this tensor power method where I start with some random vector. I have that as input to my tensor, right? Meaning I use that to contract two of the modes of my tensor, normalize and keep repeating it. So if I started at any of these eigenvectors, right, where this equation is satisfied, this tensor power method just is stationary, right? It doesn't move. So that's the same notion here of stationarity, right? So these are stationary points. And we call them tensor eigenvectors. And if you have to be really specific, they're called Z eigenvectors because there's a whole zoo of eigenvectors in general for tensors. But we won't be looking at any other kinds of eigenvectors, so we'll just call them eigenvectors. Right, so it's a lot of analogy, right? So in the matrix case, I just multiplied along one of the modes, right? So either I can do it along the rows or the columns, or the left or the right, I can multiply my matrix. And if it is one of the eigenvectors, it stays stationary, right? It doesn't move. And similarly with the tensor, I take two of the modes and multiply that vector. If it stays stationary, then it's an eigenvector. Okay, so the intuition carries so far all the way into tensors. So what is different then? Right, everything is so far, right, having an analogy. What's different? What is the nature of the equations here in the case of a matrix? What special kind of equations are they? What's special about them? What order polynomial are they? Is that polynomial? What do you think?
It's like it's a K order polynomial, right? If it's a rank K matrix.
So let's pretend they were scalars. What would this be? Is it a polynomial? It's linear, right? It's special case. It's just linear in M, right? So you don't have, it's linear, sorry, in X, right? So you don't have any of, there's no X squared, there's no X cube, right? So sorry, the equation is with respect to X, right? That's our variable we have to solve, okay? So I know you're not used to thinking of equations of vectors, right? So you're used to thinking of equations of scalars. So that's why pretend, whenever you try to take derivatives, try to reason about equations, pretend for a minute they're scalars and try to get intuitions. Okay, so these are linear set of equations, right? And in fact, this will be the key to all the nice properties of matrices. That's why this is a linear system. We know how to solve linear systems, right? So there's a lot of nice properties that come out of it. Is this linear? What is it? What's the maximum order of the polynomial here? 2, right? Because pretend this is x squared, right? That's the extension from scalar to vectors. So this is why, this is a linear operator here, whereas here you have a quadratic operator, right? It's now quadratic equations, whereas this is linear. So if I have this D by D matrix, what's the maximum number of solutions that's possible for a linear equation here? We know the answer, right? Because we know the properties of eigenvectors of matrices. So what's the maximum number of unique solutions? D, right? So if it is separated, if there is no separation, there is also that subspace, right? So we'll not look at that. Let's assume there is separation of eigenvalues. We have then D solutions. What do you think will be the number of solutions here?
D squared.
So this is the thing, right? Once you go to analyzing this in D dimensions, this could be even exponential in D, right? So that's why these are hard, right? Solving quadratic equations is hard. Solving polynomials in many dimensions is hard, right? So that's why these are all NP-hard problems, right? So we don't have a small number of solutions for this. Okay, so that's where it all breaks down, right? So the special property that with which you can build guaranteed algorithms for computing eigenvectors of matrices, right, doesn't go through. Because solving quadratic equations is hard in general. If I make no other assumptions on what this tensor T is, right, so far I've made this arbitrary, right? This can be any arbitrary tensor. So then, I don't know, right? There can be lots of stationary points. And in general, this is the problem with general non-convex optimization, right? You can have lots of critical points, you can get stuck, right, in different regions. It can be highly suboptimal. Okay, so it's hard. So are we stuck? What do we do next? So far with matrices, I only looked at first order, right, optimality. But even here, right, we didn't just have the top eigenvector, we have all these other eigenvectors also be stationary, right? So if I did the matrix power method, when I initialize it at all the eigenvectors, it stays stationary, right? But what if I initialize at a random vector? What's the result? What does the matrix power method do if I initialize it at a random vector?
It should give you the top eigenvector.
Right, so ultimately, right, so it keeps improving and it keeps going towards the top eigenvector. Right, so that means just by looking at first order, optimality, I cannot tell, right, what's going on. So that's why we need the second order. Right, so if you'll recall again this analogy in one-dimensional optimization, right? If it's only the first order, right, it's just, right, both the minimum and the maximum, right, is flat. Or you can also have this kind of saddle point, right? In X cube, if you recall, that's a saddle point there. So they all have zero gradient, but then you need to go to the second order derivatives to really tell which one is a minimizer, maximizer, and which one is a saddle point. Okay, so this is minimizer, this is a maximizer, this is a saddle. Okay, in one dimension, an example of having saddle point is this X cube, right? Because if it's at 0, it's neither a maximum nor a minimum, but the gradient is 0 there. So yeah, so now if you look at second order properties here, so we have to be careful. So if this was unconstrained optimization, I could just look at the second order condition. I could look at whether, right, I can look at my Hessian, right, I can look at whether there is, it's a minimizer or a maximizer. So I have to be a bit more careful to look at a constrained optimization, right, because I should look at in the tangent space with respect to the constraint. But roughly, right, like without going into all the details, the main idea is you can't just look at the first order optimality, you have to go to second order optimality, right? And that's what can tell us which ones are stable points, right? So I will not write it down because we are running out of time. So I don't want to start writing the equations for both the matrix and tensor case, but the intuition is the second order conditions will tell us which of these first order points are actually stable, right? So the saddle points won't be stable, right? So if you just have a little perturbation, right, the matrix power method will actually go away from those saddle points. And those that are stable will be the only ones, even with some perturbation, will continue to converge. And it turns out for this optimization problem, only the top eigenvector is stable. None of the others are. Everything else is saddle. So that's why if you ran the matrix power method, you get to the top eigenvector, right? So you can establish that by analyzing this second order condition, right? That involves the Hessian and involves the tangent space with respect to the constraint. So that's how we can establish how the optimization landscape is. And if we ran a version of gradient method, right, in this case, this power method is essentially gradient ascent with infinite step size, we can converge. So this is well established in the matrix case. The question is, in what settings will the tensor case also have some good properties? So we saw in the first order condition there is no hope, right? There's lots of solutions, so I can't possibly compute all the eigenvectors that's out there in tensors. That's too many. But the hope is, what about second order condition? The hope is if there are only few of them that are stable, then I can even run through them, right? I can just even check if there's a small number of them, which one is the top. Okay, so it's really about stability and not about, right, where the gradient vanishes. On the other hand, if we've done convex optimization, you just have to worry about first order optimality condition, right? So if you look at where the gradient vanishes for a convex function, that also tells you what's the optimal point, because there's a unique global optimal point. But then once we are in the non-convex world, right, we have to go to second order conditions to tell us which ones are stable, meaning it's either a minimizer and maximizer or a maximizer, or it's a saddle, right? So the stable points are, either minimizer or maximizer. So if I locally perturb, I can still converge. Whereas if it's saddle, if I locally perturb, I'll go away from it. It's repelling. And that's the difference. right? So that's why it's much more nuanced to think about non-convex optimization. And I know in the later lecture we'll kind of discuss more about non-convex optimization, but it's always good to ground that first with matrix analysis, right? So to me, this is possibly the simplest non-convex optimization where we can analyze, we can talk about all the stationary points, we can then ask about stability. Okay, and then we'll look at how that extends to tensors with respect to stability. So we'll do that more in the next class. Thank you.